This video is to do two things, I hope. One, I just need to kind of introduce you to lab quizzes. We have not had those in Chem 186. It's kind of unique to Chem 187. And I think the best way I can kind of, introduce this is just to kind of remind you that when you leave PCC and let's say you went to a job and they said, well, did you take chemistry? And you say yes. And they say, well, what kind of things did you do? When they ask you what did you do, you could say, well, we ran some reactions, we looked at the energy change or heat in and out of a reaction. And if they were to press you and ask you, well, can you give us an example, you could tell a story. So that's really the heart, I think, of the lab quiz. It does not cover things as far as like exact procedures, exact techniques, names. Yes, that's going to be part of maybe the story. Names of items that you use, things that are unique to chemistry, or titrations. What is a titration? Those are certainly things that might come up. But please remember, you need to be able to understand the basic gist, you might say, of a lab. So, for example, let's give two examples. We had the pennies, and we said that was used to show how probabilities leads to an understanding of entropy. Because we said, if you were to consider 6 pennies, and we said, 6 heads, there's only one way to have all heads, so it's a low probability that you're going to get that, because there's 6 different ways you can have 1 tail and 5 heads. We could have any one of those, and we did this in lab. You worked methodically to try to kind of give flesh to this idea of a macro state, 1 tail and 5 heads, could be obtained 6 different ways. You could have that, and it kind of got more crazy. We went to 15 and then to 20 ways in which you could have 3 heads and 3 tails. That was all to illustrate that probability is what's really driving entropy. Entropy just occupies all the available states, and because some states in general, or macro states, are more populated, that becomes more favored. So that's kind of entropy. So that was the story. But then you also had this idea where we had a saturated solution, and I want to pick up with this. And we made crystals out of that saturated solution, and we talked about how in lab that if this saturated solution goes to a crystallization very quickly, we saw that in that particular case, heat was given off. So this was, I'll put it in red, heat was given off. Well, if you're going to tell the story to an employer and really try to impress them and get the job, whatever it might be, it's related to science, if they were to ask you why was the heat given off, you could tell the story. Oh, because the ions that were all, you get excited and you want to be getting your nerd on or whatever. It'd say A and B got close together and they'd slam into each other and make those salts, and that would allow all those vibrations to carry out to the water around it, and that gave off heat. So we could say crystallization from a saturated solution was enthalpically driven. The formation of all those bonds in here between A, B, A, B, and A, B, all anions and cations, that was enthalpically driven. All right, so let's go ahead and get to, some more enthalpically driven. Enthalpically driven means giving off heat. So let's just do a bit more discussion on that. This might help if we split things up, because water's a key player in this. Water can make crystal formation enthalpically driven, or it can actually be the opposite and be entropically driven. And the way I'm going to illustrate this is to go the other way. We're going to go from the crystal to the solution where it's dissolved. All right, so it turns out, this, and it makes sense, I would think, that if you take any solid, I don't care if it's molecular or if it's ionic, so covalent or ionic, if you have a solid and you want to go to liquid, you're going to have to put heat in. So we would say that's entropically driven, because whenever you're putting heat into something to get it to go, and you have to put heat into it, not given off, then it's entropically driven. So you're losing from the surrounding heat as it's going to this crystal. So the surrounding is getting colder, it's losing entropy. So you better have some entropy gained from these ions getting more delocalized and spread out and going in all different directions as it goes to liquid. That's true. So if we just had the solids, I don't care what they were, you're always going to be putting some amount of heat in. They call that the heat of fusion. I know it's weird. Heat of fusion, you think means bringing together things, but in chemistry, fusion means melting. Go figure. We just try to make it hard on you. So I'm going to say that, not this is negative, I'm saying approximately 15 kilojoules per mole is the best I could find for the heat of fusion for anhydrous form of sodium acetate. Now the trihydrate, NaOAC, so sodium acetate and 3 water molecules, it's found, this one's pretty easy to find, that it takes in 20.3 kilojoules per mole of this. It takes in that much for the heat of fusion. This is, again, heat of fusion. So you'll sometimes see it this way as an F, not enthalpy of formation, but enthalpy of fusion, melting the crystal. So you would agree that if we did that and we had some watch glass, it'd be a liquid now. And it would be still OAC. I'll just put it together, OAC. But it would have the liquid form, and this one would have a little bit of water in it. Okay, great. But what we also always have to consider in the stories of things being done in water is the water itself. So it's not just in the lab that we did that we had crystals forming. They were forming in water. So whenever it's water's present, we have to consider what water's doing with those ions before you made the crystals, or going the other way. If we have the crystals and we're dissolving it, it's not just that it melts, it's that we have water coming around this sodium. So the water comes around the sodium and it makes a solvent cage. We learned about this in Gen Chem. We learned that the partial negative of the oxygen would love on the full positive of the sodium, and there's going to be some heat to that. Therefore, it's giving off to the surrounding some of that heat. This is going to be negative. You're always going to have some enthalpy of solvation, and it's always going to be giving off heat. Same thing down here, and I'll draw the OAC instead of it's happening in both cases. The OAC is going to have water around it, but now remember, if the oxygen is around the sodium, then what's going to be around the OAC that has a negative charge? I hope you're thinking, oh, water, if water is going to come in and solvate this salt, it's going to have it so that the H's are towards the negative. Why? Because the H's on water are partially positive, meaning not full, but water's very polar. So again, please understand, you have both these salts that are melting. You might say, well, split it up. We know it's dissolving, but we'll sort of split it up. You have to break up the crystal. That takes energy. Put in 15 or 20 kilojoules. But then we can also say, but there's a little bit of energy given back because it's not just melting, it's going into solution. So you get all these solvent cages made in both cases. The water around the OAC in this way, and the water around the sodium in this way. And it's always giving off energy. Delta H would be negative, be enthalpically driven. So entropically driven, enthalpically driven. So what you can say is that we have to kind of consider both the combination of these two processes. For this one, it turns out that if we dissolve sodium acetate that's in the trihydrate form, the solution gets colder. So the combination of these two is that this right here is more dominant. So this is entropically driven, right? Remember, we had to put heat in to get the crystals to pull apart, or the ions to pull apart. And this is enthalpically driven. So all I'm just saying is this is dominant. You have to put more heat in than what you get out by the solvent cage. Let me say it again. You just simply have to put more heat in at this point than what you get out through the solvent cage formed around the ions. And it kind of makes sense because it already has water in it. So it's already kind of hydrating those salts already. So you don't get much energy out or heat out as it makes the solvent cage because water is already present. So this is dominant. And this crystal dissolving takes in heat. But this crystal we saw in lab, the anhydrous form, when you dissolve it, it gets hot. So all that means is that this process, in the same way, is entropically driven. We'll just call that process A. And this process here of solvating, just like this, is process B. It's enthalpically driven. On this case, we're just saying this one wins. The energy released as all those ions are solvated by water overcomes the energy that you have to put in to break up the ions from each other or pull them from a solid to a liquid phase. So this one is a exothermic, or is giving off heat. The anhydrous solid gives off heat when you melt and dissolve it. Sorry, not just melt it. When you dissolve it, it gives off heat. When you take the trihydrate, it takes in heat. It's because you have a combination of these two factors. Breaking up of the crystal lattice, that's the first part, always takes in heat. And the solvation of the ions always gives off heat. In this case down here, this is dominant. You have to put in more heat than what you get out. But in this case up here, the solvation is dominant. It pays for and makes up even more heat than what you had to put in right here. It gives off more than what it had to put in at this point here. I hope that helps. It was probably a little bit better than what I said in lab. It's always the case. If you just tell the story a couple times, you get better at it. So I hope you're watching the video. Hope you have an understanding of this basic story, so that if you have a question in the lab quiz that hits at enthalpically driven processes giving off heat, entropically driven processes taking in heat, you can kind of tell the difference between these two and then apply it to this scenario where we have the hydrate being dissolved. It just gives off less heat than what it puts in to break up the crystals. And the anhydrous, this one, it doesn't take as much heat to break up the crystals as compared to the heat released when you solvate the ions. It releases more than what it puts in. Hope that helps. Thank you. Bye-bye.